Assalamualaikum, my name is Nur Afifah Alim binti Muhammad Amir from Group 7. My group member is Zarfan, Shazwan Nadi and Aina Aizati. I will explain about the introduction. As we know, electromechanical system convert electrical energy into mechanical energy, which including controller, sensor, actuator, plants, input and output system. So this assignment focus on designing a system that we need to meet performance requirement such as stability through systematic step like mathematical modeling, calculation and transfer function analysis. Now let's move to the plan block diagram. The given transfer function has been transformed into the shown block diagram representing the plan transfer function. The input TMS is processed by the plan to produce the output theta ms. So the transfer function illustrates the relationship between input and output in the system Laplace transform, providing a frequency domain representation. Next, for the time domain analysis of the plan based on the transfer function given here. Firstly, the natural frequency is calculated as omega n is equal to 100 radian per second. The damping ratio calculation is 0.025, which is show the system is under damp type. From this, we can derive another key performance parameters. The rise time is 0.0157 seconds, showing how fast the response can rise to 90% of its final value. The peak time is 0.0314 seconds, which when the first peak starts. Next, the delay time is 0.01 seconds, showing that it is the time to reach 50% of its final value. The percentage overshoot is 92.44%, showing a highly oscillatory response. Finally, the steady state error SSE is calculated as 0.9901, showing the system is closely tracks the input at steady state. This calculation show on the plan fast response, but clearly show that it is overshoot due to the low damping. Now let's proceed with MATLAB software with theoretical calculation. Here is our program coding. Run the MATLAB and display coding and the output at the command window. So at the command window show that the transfer function properties, step response information and the manual calculation that I showed before in time domain analysis of the plan. And then here, after we run the simulation, it display the illustration wave after we plot the step response of the system within 3 seconds. So that's all from me. Thank you.
Hi, my name is Nura Aina Aizati binti Rusli. My matrix numbers is P122310189. So I will continue with stability analysis of the plan. To investigate whether the system is stable or not, we use root-Hurwitz table by using the equation. We can see that the largest denominator is S squared. So we put all the information of the denominator in the table theoretical like this, and we will notice that there are 2 LHP in this equation. Let's take a look on MATLAB calculation. On line 1 and 2, we enter the denominator and numerator of the equation. We use the code on line 8 and 9 to determine the solution for pole 0 and apply a code at line 13 and 15 to show the backward margin. So when we run the code, we will receive 2 different figures. Figure 1 shows the 0 pole map with the 2 poles located at negative 2.5, 100 imaginary. These poles are located on the left half of the S plan, indicating that the system is stable. We can see that the damping is quite low at 0.025. This shows the system is in under damp. In figure 2, it displays gain margin and phase. It's demonstrating signal attenuation at various frequencies. The trace plot shows that the system is highly resonant but stable. Next subtopic, the general block diagram of the control system. For this assignment, we choose a closed loop feedback circuit with input controller, actuator, plant, sensor and output. We will establish the desired input value via the error detector and then the controller, which is the field circuit. In this section, the controller generates current on the actuator, which is the DC motor, and the current that flows through the DC motor produces torque on the mechanical system of the plant. Then it will flow to the sensor to ensure accuracy and performance. In the end, the actual parameters for the output will be determined. Next, look at the controller's electromechanical drawing. In the previous section, we state how we build a circuit with various electrical and mechanical components to ensure its reliability. On the left side of the diagram shows there is an electrical circuit component, which is the field circuit that will impact the DC motor at the middle throughout the mechanical system. We designed a series circuit using a variable resistor, 2K ohm resistor, an inductor, and 6 capacitors. This RLC can be considered a part in the system. Then, load used to convert all the electrical energy into mechanical energy. On the right side, the mechanical system components are shown, including a spring for flexibility, displacement, and mass for the inertia of the moving part, 2 damper that add friction to the motion, and a sensor as tachometer that can be improved the system stability at high speeds. This block is designed to highlight the dynamic stability and response of the systems. That's all from me, so I will pass to another analyst to explain about other subtopics.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zafar Barazif, managing number B122310050. So now I will present about the hardware costing. So we use 1 resistor, 1 inductor, 6 capacitor, 1 mass, 2 damper, 1 spring, 1 low back EMF DC motor, which is actuator, 1 high feedback tachometer, which is sensor, and 1 variable resistor 1 ohm to 100 ohm, which is a controller. So the total of hardware costing is RM53.80. Next, for mathematical modeling. So first thing first, I want to apologize to Dr. Mania because in the report was I submit have some technical issue folder and overall transfer function. So at this video I will explain the truth of mathematical modeling and OTF. So this is the controller for equation from field circuit. We use 2 kilo ohm, 1 micro henry, and 6 capacitor. The value is 1 millifarad. So capacitor in series, we get the 6/1 millis, and then 1 millis multiply with resistor and inductor, and then multiply with 100, and then we get this equation for control. And then next, for actuator, the component we use is low back EMF DC motor, which is the value is 7.5. And then this equation for plant, which is mechanical system. So we use 1 mass, 0.01 kilo, 2 damper in series 0.1, we get 0.05, and then 1 spring, the value is 100 Nm. And then we substitute the value inside this equation, then we multiply with 100 to get back the original equation of the plant, which is mechanical system. And then so for overall transfer function in the report, as I mentioned, have technical issue. So this is the truth of OTF. So this is the closed loop, and then we perform the cascade for controller, actuator, and plant. We get this feedback, and then we feedback the sensor, we get this value, and then we simplify. After simplify, we multiply with 1/s. So this is the truth of overall transfer function from our assignment. And then performing Mason rule to verify our answer, to check if the OTF is true or not. So first is converting cascade block diagram to signal flow graph, and then draw all the node signal, and then draw all the branch system, and then Mason rule component. So we get 1 forward gain, substitute the equation and simplify. 1 loop gain, substitute the equation and simplify, and we get 0 non-touching loop. And then find the transfer function we use the formula forward load gain over 1 minus sum of load gain and substitute the value. We get this, and then we simplify. So the mentioned rule, we get 75 over 1 multiply 10 power of negative 9 s power of 4 plus 2 s power of 3 plus 3819 s power of 2 plus 20030 s plus 60,000. So it will same like OTF value. So that's all from me. Thank you.
Hello, my name is Muhammad Shazwan Hadi bin Selamat Alimi, matrix B1223109094. So now I will continue for the number 10, times domain analysis for the control system. So this is the MATLAB we use for the time domain analysis for the control system. So just run. This is the overall transfer function we got, and this is the state response for the control system, time domain analysis for the control system. This is the state response, and we got the underdamped state response. So this is the parameter we got for the time domain analysis control system. The TR, settling time, TS, settling max, which is the Cmax, the overshoot, peak time, TP. This is a TD, and this is for the SSE. So now for the 11.0 stability analysis of the transfer function. So this is the OTF, and we apply the Roos-Lewis criterion. So for the Roos-Lewis criterion, we just use the denominator. So the higher denominator is s power of 4. So we just use the s power of 4, s power of 3, s power of 2, s power of s1, s power of 0. So we got here the positive, and for the s1 is also positive. So there are no change for the answer. So the RHP is a 0, which is all the positive. So the LHP is 0. So for the LHP, it is the higher power of 4. So the LHP is 4 minus 0. So LHP is 4. So next, for the 11.1 comparison of the time domain analysis. So this is the table of the comparison. So this is the time domain analysis of the plan, and this is the time domain analysis of the control system. So the rise time, peak time, settling time, percentage overshoot, and the Cmax for the comparison. So this is a comparison, the plan and the control system. So the percentage overshoot for the plan is 92.44%, and the time domain analysis of the control system we got 6.2598, which is the set response is stable. So for the MATLAB result, stability. Okay, so this is the box plot we get in phase margin for this for the magnitude from the frequency radian. So 98.1, negative 98.1. So this is the gain margin 114, the frequency is 100, and the closed loop is stable. So in conclusion, the transfer function characterizes a second order system with specific damping and natural frequency, illustrating the tension and steady state behavior. The block diagram identifies feedback loops and input-output relationship, while time domain analysis highlight key parameters like rise time, settling time, settling max, overshoot, and so on, showing the system is underdamped. Stability analysis confirm all poles have a negative real parts, supported by the Roos-Lewis criterion, indicating stability. A box plot reveals a frequency response and performance limitation, and the MATLAB simulation validate the system state response. Additionally, cost estimation confirm the feasibility of the design. Last but not least, the designing of the electromechanical control system integrate electrical, mechanical, and the computer science skill, optimizing performance and deepening system understanding. That's all from us. Thank you.